Okay, so yesterday we started discussing non-degenerate three forms, right? Remember, we say that a three form is non-degenerate if so V is here isomorphic to R7. If you plug in two linearly independent vectors to this thing, there is a third. You can find a third vector such that the when you also plug that in as the third component, third input, the whole thing will be non-zero, right? So that was the definition of non-degenerate three form. And yesterday I said that whenever we have a non-degenerate three form, we can actually get a metric and the volume form that corresponds to this to the non-degenerate three form. So today we will just start with that and quickly move on to representation theory. So the proposition is given non-degenerate three form, we may associate a symmetric bilinear form and a volume form on V. By the way, this almost works over complex numbers as well. There's a little bit of an ambiguity there. To avoid that ambiguity, you have to start with a volume form. But so the proof of this is basically just the equation that we used yesterday, but we use that for a specific non-degenerate three form. So this time we will look at this equation for this arbitrary non-degenerate three form. I will use lowercase b here because a priori we don't really know what kind of properties it satisfies, whether it's basically behaves like whether it's non-degenerate and so on. But actually, okay, it's easy to prove that. So this is the equation that we would want to consider. So here, omega is a volume form, and B is a symmetric bilinear. And using non-degeneracy of beta, you can prove that actually, if you choose a non-zero volume form, this B will be also non-degenerate. We will skip that. That takes a little bit of time. Perhaps you may want to do that as an exercise. But so now we just want to show how to construct these two in a sort of unique way given beta. So what you want to do is, of course, the space of 7 volume forms is just one-dimensional. So at the beginning, you just pick one random volume form. Okay, so you fix this thing, and then every other volume form is c times omega for some constant c, right? So if you plug in c omega here in the place of omega, this equation actually uniquely determines a b. It's a symmetric bilinear form, and as I said, this gives you actually a well, actually, okay. Before that, let's say that we fixed an omega. We plugged it in there. That determines a b. Okay, so this gives you a b. Okay, it's symmetric bilinear and non-degenerate. That's an exercise. And then if you, instead of omega, if you plug in c omega, of course you will just get 1 over c b. So that gives you a metric. By the way, when I say metric here, I just mean, again, just the non-degeneracy. It can possibly have a signature. And now that you have a metric, you can compute the norm of C omega using this metric, norm squared. Using this metric here. And the condition is that you want this to be 1. So this is something we impose. And this in terms of the initial two things that we obtain, omega and b, this is actually somewhat similar to the previous, the calculations that we did yesterday, but perhaps in a certain way it's actually easier. This is actually seated in line times omega squared with respect to b, and you want this to be 1. So in this case, there exists a unique C satisfying this equation. And well, of course, once you have a unique C, there's a unique volume form and a unique metric.
This calculation we only did, right?
Yes,
That's the most tricky part, getting it.
No, actually, in the calculation that we did yesterday, it was, tricky, but actually, it's not very hard to compute, like just the norm of C omega squared with respect to 1 over CB in terms of omega squared B. Because basically 1 over CB affects makes the norm of the vectors scale by 1 over square root of C. So it's on the 7th exterior power, it's like 7 to the, it affects as the power to the 7 over 2. And then on volume form, it puts a negative sign. And because we're looking at norm squared, it just becomes to the negative 7. And then because there's also a scaling coming from this, there's also a scalar here that because this is a quadratic form, you can also take it outside. So overall, it gives you a, that part is actually not very tricky. Like it's easier than the competition that we did yesterday. And okay, so we got these two, but of course you might ask, like, what if we start with something else? Like if we start with some other volume form here, are we going to get the same things? And that uniqueness part is an exercise. That's not a very difficult exercise because, if you just pick a different omega prime, let's say, this will just be there will be just a constant k, so where k times this is equal to that, and then you can just work it out, and you will see that you get the exact same volume form in the metric. So this is how you. By requiring this, basically, you get a unique volume form in the metric. So, so here, actually, I would say that the tricky, perhaps computationally, the longest part is actually to prove that this is non-degenerate, which I skipped. But again, as a remark, let me tell you that the metric you get maybe of signature 3, 4 or positive definite. We will mostly consider just positive definite metric, and if you get positive definite metric, beta is called positive. This 3 form is called positive 3 form. We will mostly work with positive 3 forms. Like in the future, once we start talking about G2 manifolds. And And for the signature 3-4 metric, actually there's a very analogous story. And actually the stabilizer group, I mean, if beta gives you signature 3-4 metric, then the stabilizer group of beta is actually called split G2. It's one reincarnation of G2. But again, so as I said, like there's an analogous theory there, but we will not really discuss the details of that. It's non-compact real Lie group. It's we'll not discuss that almost at all.
I mean, this your vector space is C7, right?
No, so here it's R7.
R7.
Yeah.
So how do you get 3-4 positive? I mean, here you get positive always.
No. I mean, the
3-4, at what point you get this two alternatives appearing in the program?
oh, I mean, it depends on the very beginning, like this beta here. There's a different, like there's a, one sort of class of non-degenerate 3 forms which give you positive definite metric, and one class of non-degenerate which give you 3-0, 34.
Another class degenerate.
Yeah, degenerate ones. Yeah. Yeah, exactly. And actually, like I again want to point out to the similarity between. So I mean, over complex numbers, actually. I mean, so there's an ambiguity there. Like as I said, basically you have to choose a volume form, but once you choose a volume form, like everything is determined by that equation anyway. But I'd like to point out to the similarity to the fact that, again, over real numbers, there are 2 types of octonions, and over complex numbers, there's only 1 type of octonions. So like, that you can also sort of see these alternatives there. So these are, the fact that there are only 2 of them are deeply related to the fact that there are only 2 types of octonions. One is the octonions that we saw, the other is the split octonions, which is actually very similar to the definition that we saw. It's just the metric is different. And
is there a quick way to see that these non-degenerate 3 forms have 2 chambers, positive definite 3 form?
I mean,
some soft argument is that.
I mean, no. Like the only argument is actually to actually construct from this beta an octonion algebra, and because octonion algebras are classified, I can. Yeah, that's the only way. Yeah.
You can't help by looking at the non-degenerate 3 forms.
I mean, no. I mean, so basically, after this process, you have beta, and I mean, so you have a metric. So using that, you can define a cross product, and you can, from there, you can actually identify this space, this 7 space with the imaginary octonions. Actually, like you can choose a basis so that it matches with exactly the imaginary octonions with the I, J, K, L, and so on. Like these. All these relations are satisfied. So basically, as soon as you have such a beta, like for example, positive definite beta, you can. This is actually in every way isomorphic to imaginary octonions. There's no distinction. Like it's just any distinction is just due to the change of basis. Yeah, I mean, so once you have I mean, of course, once you have a metric, you can define a cross product on V. By Now, using this equality the other way around this time, and like basically this gives you, I mean this makes V basically imaginary octonions. Yeah, so like if there are no questions, I will actually move on to the representation theory. It will actually seem like a detour for a little while because we will be I want to like quickly give a crash course on like SL2C representation theory, and then talk about like how it's related to, I mean, how that helps us. Well, what we can do about G2, what we can say about G2, and then from there we will do one sort of example, like sample calculation. Although the details for G2 can get a little bit more complicated, so I will mostly focus on SL2C. And then at the very end, we will actually also give a little bit more geometric and yeah, we will just give a little bit more geometric information. Okay. So the purpose of this part is actually to give you like a working knowledge of this representation theory. And here in this section, we will actually work with complexified Lie algebras, but we're not really losing anything because we will be working with simply connected Lie groups. And when you're working with like the representation theory of simply connected Lie groups is basically the same as their representation theory of their Lie algebras or their complexification. So that's why we want to. So basically, the representation theory of this SL2C is the same as the group SL2C or SU2, for example. SU2 is the corresponding compact object, compact group that corresponds to this thing. It's not SL2R. But in any case, that's not a super important part. So let me just quickly write down this. Of course, SL2C is the set of 2x2 matrices whose determinant is 1. And if you linearize this, equation, the equation you get is a set of 2x2 matrices whose trace is equal to 0. So traceless 2x2 matrices. We usually use x equals 0, 1, 0, 0, y equals 0, 0, 1, 0, and h equals 1, 0, 0, negative 1 as basis of this algebra. From now on, for a while, we will say, like, we will call the eigenvalues of H weights, eigenvectors weight vectors, eigenspace weight spaces, and so on. So. This is a little bit of abuse of terminology, but I just like we don't want to cover all the details. So so eigenvalues of H are weight vectors. Weights. Eigenvectors. Weight vectors. And eigenspaces, weight spaces. Okay. So it's just basically replace all eigens with weights, almost. Okay, so what's an Lie algebra representation? Let me quickly give a definition of that. So, given a Lie algebra, by the way, I mean, of course, the I mean, here over the group, you just have the usual, matrix multiplication. But once you pass to Lie algebra, the right notion of multiplication becomes this Lie bracket, right? X, Y, the bracket of xy is xy minus yx. It's just the commutator of these matrices, right? So okay, so for given Lie algebra G, a linear map rho from G to endomorphisms of V, I mean, let's say complex linear, is called a Lie algebra representation if rho of the bracket of xy is equal to bracket of rows. And this is by definition, again, the commutator of these two. So we'll stop writing this row over and over again. I'm sorry, can I have some water?
Yeah.
So yeah, we will stop writing this row over and over again. So instead of writing this, we will just write xv. And also, when we say something's a Lie algebra representation, we will not use this whole notation again. We will just choose, we will just say that V is a Lie algebra representation. But actually you should understand that there's this whole row here, okay? So that will be implicit. And at this point, let me just quickly tell you what it means to be irreducible. Basically, we say that representation is irreducible if there's, okay, well, it's just easier to write it in symbols. So called irreducible, well, maybe let's say well, let's define reducible. It's called reducible if there exists V which is not equal to V, which is not the 0. So there's a proper subspace, that non-trivial subspace, such that rho G of W is inside W. Otherwise, we say that V is irreducible. Okay, so we said a lot of words, but now we'll, perhaps inspired by Selman, we will start drawing some pictures. So we'll, well, first of all, we wrote these three matrices which I just erased. But if you compute the multiplications there, you'll see that hx is 2 times x, hy is negative 2 times y, and xy, the bracket of xy is h. Okay, so we will, on a diagram, we will denote this like this. So we'll put a number line here. We'll put negative 2, 0, and 2. We'll put y here H here and X here. Okay, so here, these are the weights of this representation. I mean, in this specific case, these are sometimes also called roots. But again, I don't want to use that word. It's just weights. So we have, I mean, the reason that I'm doing this is basically, if you look at this, you see that when H acts on, I mean, X is an eigenvector of, or weight vector of H with weight 2, right? So that's what this symbolizes. And similarly, Y is a weight vector of weight -2. So that's where this is. And of course, if you take bracket of H with itself, it will be 0. So that's where it is. Let's do another example. Of course, this is 2x2. These are 2x2 matrices. They act on C2. C2 is an SL2C representation by usual matrix multiplication. Note that when H acts on E1, the standard basis vectors, the first standard basis vector, it's just E1. And when it acts on E2, it's just -E2. So, and moreover, when X acts on E2, we get E1. When X acts on E1, we get 0. When Y acts on E2, we get 0. When Y acts on E2, we get E1. So we can describe all of this information by using this diagram, which will be very similar.
Y acts on E1.
What is
the last line?
Oh, well, yeah, sorry, yeah. Yeah, thank you. Okay, so now we can draw this diagram. So I will again use this number line. We only have two weight vectors and 2 weights, so one of them is -1, the other is 1. On top of this sits E1, and on top of this sits E2. Now note that, so X takes E2 to E1, and Y takes it back. And you can also sort of augment this picture by saying that if you act on E1 as well with X, you'll go to 0. And if you act on E2 by Y, this will also go to 0. So you can sort of describe this representation with this picture. Okay? And in fact, you can sort of say something similar here.
Except it's not the algebra.
What is it?
And the second one is not a real algebra representation.
This is this is also the algebra representation.
What's the difference between these two? What's the real algebra structure of C2?
Well, no. Endomorphism, like we want a Lie algebra structure on the endomorphisms of the vector space.
Yes.
So it's and of course, like endomorphisms have, commutator. Yeah. So, okay. Well, all right. So, I mean, of course, both of these are irreducible. Of course, there's no subspace that sort of gets sent to itself, but if you act on it with the whole SL2C. And actually, we can sort of extend this observation that we have here. Let V be a weight vector. By the way, I should perhaps also say this. I mean, the reason we're focusing on SL2C is not, I mean, so actually, like in a given semi-simple Lie algebra, you can actually find many SL2C triples, as they say, which means basically you can find a subalgebra which is isomorphic to SL2C. So if you have a representation of that, you can actually restrict to that subalgebra to understand to answer some questions about that representation. So like the reason we're focusing on SL2C is actually not arbitrary. SL2C actually plays a great role in representation theory. It helps you in many ways actually. So this is not like a random example, like random choice of algebra, just because it's simple or anything. So the things that we're doing right now will have sort of equivalence in G2 representations as well. Okay, so let V be a weight vector of weight n. If xv is non-zero, then it's a weight vector of weight n plus 2. Similarly, if yv is non-zero, then it's a weight vector of weight n minus 2. And proof is, both cases are very similar, so let's just do one of them. So here, if I'm just writing this down, what I mean is I'm first acting on v with x and then with h. Okay, so this notation just means this. But I don't want to keep writing in parentheses all the time. So this, by definition of being a Lie algebra representation, is actually the same as this action, which is, okay, so we know what hx is, that's 2x, so that's 2xv. And then we have x hv, so first we apply h to v, and we assume that v is a weight vector of weight n, so that's n times v, and then we have x, so plus n xv. So overall we have n plus 2 xv. So we see that xv is a weight vector of weight vector of weight n plus 2. And very similar computation also works for yb. So it just reduces the weights by 2. So this is not a coincidence. Like x increases this by 2 and y decreases by negative 2. Decreases by 2. All right. Okay, here's one fact, which is not very difficult to prove, but we will again skip that to save time. You can read about this in Humphrey's Lie algebra representation, Lie algebras and their representations book. So let V be a finite dimensional, finite dimensional, irreducible SL2C representation of highest weight k. We didn't define what it means to be highest weight k, highest weight, but I guess that, I hope that's sort of obvious. In a given representation, you have this number line, you just pick the one that is like the highest, right? That's all. So we have a highest, we have a finite dimensional reducible representation of highest weight k. With highest, with highest weight vector V naught. So x V naught is 0. I mean, of course, being highest means x V naught is 0 because if it's not 0, then there's a higher weight, right? So this just follows from this proposition. We have this like highest weight V naught, and then we define the I plus 1 to be y vi for I greater than or equal to 0. So here, I mean, in this fact, I'm trying to tell you what all the irreducible representations of SL2C are. I mean, first I'm writing in words, but actually I'll just quickly draw a picture as well. Hopefully, you know, at least in that there it'll be more clear. Well then, okay, so Vi equals 0 for I greater than K. Vi is a weight vector of weight k minus 2i for k minus 2i for I between 0 and k, and the set from v0 to vk form a basis for v, and hence it's k plus 1 dimensional. Okay, so the picture is you have this k up here with v naught here, and then you have this k minus 2, you have a weight vector at k minus 2, k minus 4, and so on. So here we call this v1, v2, this is y v naught, this is y v1, and so on. And then it stops here at the negative k. And this is negative k plus 2. Right, this is vk, this is vk minus 1. All right. And like something similar happens is as you go left by multiplying with y. And you go right by multiplying by x. And this is 0. So overall, like a finite dimensional irreducible representation of SL2C looks like this. There's the highest weight k, and the lowest one is also is exactly negative k, and there's one dimensional. I mean, each weight space is exactly one dimensional. So there's each one of these dots represents a one-dimensional weight space. Okay, and in this picture, we take the generators to be v naught, v1, v2, and so on. But actually, okay, this can be a little misleading sometimes. Keep in mind that because of the way we define these VIs, right? Like here, you go from one vector to the other one. I mean, to the one on the left by multiplying by y. But if you multiply by x, you may not get to the exact same vector. You may get to a multiple of that vector. Okay. So when you look at this picture, you shouldn't instead of thinking that y takes this vector to this vector and x takes this vector to that vector, you should be thinking that, well, y takes this eigenspace here to this eigenspace, and this x takes this eigenspace here to this eigenspace. And also these dots here can be representing maybe just the weights or the corresponding. I mean, this sometimes causes confusion. I will be using these dots to represent three different things. Okay, so you should infer which one I'm using from the context. One of these things can be weights. One of these things can be the corresponding weight space, and the third thing can be a basis element of that weight space. Okay, so it can be any one of these three things.
So why is the basis?
Sorry? Oh, why is this a basis?
Yeah, why form a basis?
I mean, basically, you first find like highest weight vector. So say that's x naught, and then I mean, first of all, like, by this proposition, they have different eigenvalues, so therefore they are linearly independent.
Yeah,
right? And then, so if you keep applying this y over and over again, I mean, at some point it has to stop because it's finite dimensional.
Yeah.
And then when you apply x, you can prove that the result will be a scalar multiple of this one. So it cannot go anywhere else. Like there's no way to jump somewhere else.
Yeah, you need to show this is closed under.
Yeah, exactly. It's closed under. Yeah, exactly. You can actually prove this as an exercise. Yeah, like it's not super difficult. Yeah.
So what's the weight n? Give a definition of weight n again.
Weight n. So this is. I mean, here I'm not.
Apply h or any.
H.
Only
Yeah, it's always
Only
H. Yeah.
So h of beam is n times.
Exactly. Yeah. So yeah.
So another question quickly.
Mhm.
So you consider complex representation? I forgot what you said.
That's true. Yeah. I mean, here I'm working with complex Lie algebras and complex complex representation. Okay, so they all look like this, and in fact for all k, also maybe let's add that as a fact. For all k in Z, like that's non-negative, there exists a unique irreducible representation of SL2C.
All weight spaces are one-dimensional. It's just a specific.
Exactly, they're all one-dimensional. As long as it's
only for this example, right?
I mean, this is an irreducible example. Yeah. Of course, if it's not irreducible, there can be multiple or. I mean,
cannot be greater than one dimension.
For irreducible SL2 representations, no. SL2C representations, no. I know. Fine. Yeah.
You change the algebra, then you can produce more dimensions.
Right. Yeah, that's true. We will actually.
But loops are always stays one dimension.
Almost. Well, yeah, we will discuss that. Yeah. Mm-hmm. Actually, the pictures are already over there, but we'll discuss that more. So, okay, how much time do I have, by the way? It's like 20 minutes, maybe?
17.
17. Okay. All right. I mean, let's quickly discuss. What?
Like 5 minutes.
What is it? Yeah.
Start 5 or 10 minutes late.
Mm-hmm. Okay. I mean, let's also define some induced representations quickly. Given representations V and W, we can form new representations. So dual representation of V is, we denote that by V star. And here the action is X acting on F is, well, okay, let's plug in a vector. F minus F XV. I mean, of course, because we're talking about dual space, I'm plugging in some vector to the new element of the dual space, and the result should be this one.
What's F?
F is an element of here, so F is an element of V star, and V is an element of V. Well, okay, maybe instead of X, because we're already fixed X, Y, and H, let's say Z here to denote an arbitrary element of SL2Z, or like arbitrary element of G. Okay, so that's the dual representation of V. We can form like a direct sum. Yeah, actually, I mean, it doesn't work otherwise. Like, so if you just try to make sure that that bracket relation, holds in the definition of Lie algebra representation, it just, you need a minus sign there.
Usually the representation serial algebra.
Oh, yeah, it's like Lie algebra, yeah. So the direct sum of, direct sum representation, V plus W. So if I take V, comma W, I just act on it as a ZV, ZW, or perhaps you prefer a different notation. It doesn't matter, of course. Like it's the thing that's clear. And let's also write tensor product, and perhaps this will be the most important one to us. Z acting on V tensor W will be ZV tensor W plus V tensor ZW. I mean, in general, like as a motto, you can sort of think of like Lie algebra as I mean, of course, Lie groups are like manifolds, and like the Lie algebras are the tangent spaces. So like everything in Lie algebras looks like derivatives. So this is like a Leibniz rule, right? So, and this is like the usual editor rule for like derivatives and so on. So these rules look like that actually. Okay, so I mean you can form other things, like for example you can look at the alternating or symmetric tensors of V, but of course I mean the action will be basically given by this. I mean you may just replace this with wedge here and they will all be wedge. But formally it's exactly the same. So I will not write that. And also, if you think about homomorphisms from V to W, at least in the finite dimensional case, this is V dual tensor W. So you can use these rules to construct this representation as well.
So basically, if we think about it, then this is just when you have a Lie, you have a representation. Think about a corresponding Lie group action, vector space, and this is a canonical way to construct.
Yeah, exactly. So yeah, there's one-to-one correspondence, and it's given by like if you go from Lie algebra to the Lie group, it's given by the exponential map.
Yeah, the exponential map, right? And then you have
Yeah, it's the natural thing. Yeah, exactly. You basically just look at the action of the group, take its derivative. Yeah. All right, so here's one more bit of a notation especially for irreducible representations. So let V be SL2C as a representation here, and W be C2. These are the two representations that we saw earlier. Then let's draw a picture of the following direct sum representation. So this is of course v plus w plus w plus w. So we draw the diagram of this as follows. So v had weight vectors at 2, probably 0, -2, and w had weight vectors at -1 and 1. Because of these multiplicities, we have 2 copies of this. So we put this dot, but then we just put a circle around it to represent that the multiplicity is 2. Similarly here, and then this is 3 times, so we will have dot and 2 circles. I mean, if it gets too bad, we might write some number here, like 3, for example. Okay.
Explain this slowly.
Okay. So remember that, like the picture for v was this. Just 1 dot here, 1 dot here, and 1 dot here. Like this was v, and w was just 1 dot at -1 and 1 dot at here. So if you take 2 copies of v and 3 copies of w, this is how we show it in the picture. Like to denote the multiplicity, we just put another circle around these.
When you put a 1 circle, multiplicity 2.
2, yeah, because it's dot and the circle.
I see.
Like the first dot represents 1 element, the second dot represents a second, like 2-dimensional basis. I mean 2-dimensional eigenspace. Well, what is it? Oh, I mean, like if presumably you can have like 15-dimensional points, like multiplicity of 15. We will not draw like 15 circles. We will just write a number. Yeah. And you can put a 2 here as well. Just like if it gets too complicated. I mean, actually in this class, today it will not get that complicated, but just as a convention. All right.
Is it possible that they coincide at the same point?
Coincide? I mean, yeah. Like I intentionally draw this in a line with each other. Yeah. I mean, sometimes I will think of this as like a superimposition of these 2 with multiplicity, 2 here and 3 here. Like we just put them on top of each other.
So like Mustafa said, once you put the circles, there's a high-dimensional vector spaces here.
Yes, exactly. But still, if you pick a specific weight vector here, the irreducible representation that it sits inside just looks like this, actually, like that by itself. Yeah. That's actually a good way to think about it, because sometimes we'll also sort of think of this as like removing like this representation, like 3 dots and 2 dots perhaps, and things like that. But okay. So here's a quick exercise. Let V and W be SL2 reps. V in V and W in W be weight vectors of weights N and M respectively. Then V tensor W in the tensor product representation is a weight vector of weight N plus M. So if you have 2 weight vectors of weights N and M, their tensor product has weight N plus M. Okay. And of course, because this holds for tensor products, you can also show that it holds for, exterior, wedge products, and so on, like any kinds of tensors. Yes, actually, yeah, we will also see that as when we go past to G2, we will think of that rule as generalization, like immediate generalization of this rule. because this exercise only depends on the h, so to speak. Okay, that one element. And in G2 we will have two of those later. Okay, so, and one last fact. So any finite dimensional SL2C representation is direct sum of irreducible representations. So now we'll do two more examples here, and then we'll move on to G2. I mean, our discussion in G2 will be much more like short actually, but like the main ideas are all here actually also. I mean, well, at least the part that we can cover.
Good question.
Uh-huh.
So when you talk about representation and everything,
Mhm.
so the weight seems always integer. Weight is the eigenvalue, right?
Yeah, that's true.
Why is it always integer?
Because you said change by 2 plus minus 2.
Yeah, but yeah, that's true. But like, why would it? Like, his question is sort of like, why does it start at an integer? Like, why doesn't it? I mean, actually, it is possible, but those are not finite dimensional. Like, it's possible to have non-integer weights, but they immediately become like even the irreducible representations are infinite dimensional. So we're just not covering them, basically.
Yeah, but why?
Oh, why?
Yeah.
Okay. So you can actually, using these commutator relations of SL2C, you can sort of see you will see that if you apply, well, like, I mean, so if it is finite dimensional,
Yeah.
then after a while, I mean, okay, let's. Okay, maybe I'll try to answer that like after the talk. I need to make up my mind.
So the question is, if you have finite dimensional representations, why the weights are integers?
Right. Yeah. Mm-hmm. That's the question. Mm-hmm. Right. I'll try to answer that after the.
I guess you play around with this relation x, y, h, right?
Yes, exactly. Yeah, they all come from there. Yeah. Mm-hmm. Yeah. So again, V is SL2C, W is C2. We consider V tensor W. So we can actually, like, using this exercise. I mean, so what we want to do is we want to decompose this as a direct sum of irreducible representations. We know we can do that by this fact, and V tensor. Yeah, this fact here. Yeah. And we will. So what we can do is we already have a basis of V and W that consist of weight vectors, and we can form a basis for V tensor W by just taking pairs of those things, pairs of eigen weight vectors, right? And we know what the corresponding weights should be from this exercise here. So that actually tells us how to so this is W, this is V. That actually tells us what the diagram should be. So we're tensoring these two. So, I mean, of course, we have to pick one vector here and one vector here. So look at all possible pairs like that. So if we take this two, that will give us a vector here at 3, for example. All right, maybe let's give those things names. Okay, they already have these names. So E1, E2. So this vector here corresponds to X tensor E1, for example, in our notation. These two, the tensor product of these two. These two will give us 1. So that's X tensor E2. And then these two will give us also 1. Well, maybe let's write them. Okay. So X tensor E2. So this is x tensor E2 and also h tensor E1. And we will have -1 twice, very similarly, h tensor E2 and y tensor E1. And we'll have 3 once, y tensor E2. So we put all the basis vectors there, and we see that we have this diagram, which is of course a superposition of 3, -1, 3, 1, -1, -3, and 1, -1 and 1. So we see that this representation, actually V tensor W, is a V1 direct sum V3, where Vk is the irreducible representation of highest weight K. Yeah. So just by looking at this picture, like just by playing with these, diagrams here, we can immediately tell that this tensor product decomposes like that. How much time do I have right now?
You don't.
Oh, I don't. Okay. Okay. I mean, you can do something very similar with like the exterior powers as well, like the lambda 2 of V, for example. Let's leave that as an exercise, maybe. So decompose lambda 2 of V. Let's leave that as an exercise. Actually, okay, it's in my notes, so don't look at my notes if you're doing that exercise. It's a very similar idea. And basically, you just need, once you write down the diagram, you just have to figure out how to, you just need to express that as like the superposition of these various irreducible representations.
We only know how to work tensor products, so lambda 2V, we write this like.
Yeah, I mean, so
Tensor V minus.
formally they are exactly the same. I mean, so they work exactly the same. The only difference will be now because you're forming an exterior product of V itself. You're not supposed to, when you're taking pairs of vectors, you're not supposed to pick the same vector twice. You just pick distinct pairs, and then it's otherwise it's.
There's a commutative change in minus.
Well, yeah, but the weight doesn't matter, like as the weight space, yeah. Okay, then I'll stop here, and tomorrow we will basically use these ideas to answer some questions about G2. And it seems like I didn't get to use these pictures. Yeah.
Is it why E2 is 3 or negative?
Which one? Oh, -3, yeah.
Okay,
Yeah.
that's them to speak.
Okay.